Okay.
We're going to get started. Hello and welcome. This is our webinar looking at the new scanning system from GOM. This is the GOM Scan 1. My name is Ben.
My name is Josh.
And yeah, we're going to be taking you through a couple of different applications for this system. So this is, as I say, new scanning system from GOM. It's an entry-level scanning system. There's a couple of different variants. So we've got the GOM Scan 1 400, which we'll be showcasing first. That refers to the measuring volumes. This is really for larger components. And then we'll be using the GOM Scan 1 200, which is for smaller components. We can get much higher resolution. And we're looking at some engine components for that, which we'll be scanning in a second. There's also the 100mm, which is smaller still, and that's for really fine resolution on small components. But we're talking about a couple of different applications. To start with, this propeller, scanning this, looking at reverse engineering it, inspecting it for defects, and maybe recreating it in applications that way. But I'll pass it to Josh. He's going to take us through this first application.
Great, thanks, Ben. Just before we get into it, if anybody has any questions at all during the webinar, just feel free to use the chat window in the screen. But yeah, we'll get into it.
Yeah.
Also worth noting that all of this technology that we're showing here is for sale as well as for service. So if you're interested in having a component scanned, we can do that for you, as well as offering these to you on a sale basis. I'm going to share my screen so we can get stuck into it. Great. Okay. So this is the GOM software. So what we're seeing here in the top left of the screen is the live camera feed. So I can switch here to both live views. So you can see the left camera and the right camera. You can see they're both looking at the same area of the component. And if I just switch back to the left camera feed only, we can see here, this is the 3D view. So this is the measurement volume the scanner is seeing at any one time. Okay, so we can see these green dots within the measurement volume. These are reference points that have applied to the surface of the component. Okay, this will help us keep track of where the measurements are positioned relative to each other. And it will also help us for the second stage of the scanning process, which is marrying the first side to the second side based on the common reference points that we'll be seeing. Okay. So for the scanning today, we're scanning this propeller. This is a very worn and beaten up propeller. So this is for a maintenance repair application. But what we're really going to be doing with the scan data, once we've created the digital twin, is reverse engineering it and creating a CAD model which is going to be used for production. Okay, so we'll talk a little bit more about that at the end, but right now we're going to jump straight into it. So within the software here, I've got this workflow assistant. Okay, and the workflow assistant basically guides us through how to scan if we're a little bit unfamiliar. Okay, but I can just start here scanning with rotation table. So I'm going to click that. Choose the measurement temperature. I've got it set to 6 measurement positions, which is good.
Yep, perfect. 20 degrees in here. Nice temperature control.
Perfect, 20 degrees, that's right.
Lovely.
So what's happening at the moment is the scanner is projecting a pattern across the surface of the part, which the left and right cameras are looking at and triangulating, and this builds up our 3D surface map. So we can see that's the first patch of data that we've collected. The ROT 350, which we've got connected to the computer as well, rotates between each measurement, so that provides a semi-automated setup where we don't actually have to do much interference. Okay, so while that's happening, we can see the data being built up on the screen. What we will have to do after we finish capturing these first 6 measurements is delete the background data. So what we can see at the moment is we can see that the scanner is capturing everything. We can see it's capturing the propeller, which is the region of interest for us. We're also capturing the rotation table, the ROT 350, which is rotating, as well as the background, the table the ROT 350 is sitting on. Okay. But as we mentioned, this is for production application. So we're going to be reverse engineering to create a CAD model. And this CAD model can be read by any manufacturer for any sort of manufacturing application.
Could be 3D printed.
Could be 3D printed. A little teaser for what's coming up. Okay, so we can see here we've captured the first set of data from this first side. It's nice clean data. So what we're going to do now is delete the background. So I'm going to come up here and say cut out points. Okay, and I'm going to say cut out below plane. I'm just going to define 3 points in the rotation table to define that plane. We can just have a quick check to make sure that that's good. And looks pretty good. So what we're saying is that anywhere from that plane down, we're not going to accept the data and the measurements that we've just captured. Excellent. So we're going to do that. Okay, so we finished scanning the first side. So we're going to flip the propeller over, and we're going to continue measuring the other side. Make sure it's in the middle of the rotation table. Again, from the workflow assistant, we see prepare scanning a second side. So we're going to do that. And again, we've got a new measurement series within the software. Okay, so we're going to just click scan again. It's going to repeat that, just collecting data from the other side. So once we've collected all the data and we're happy with the scan data that we've collected, the next step will be taking the scan data out of the GOM software and into a reverse engineering software called Geomagic Design X. And what Geomagic is going to do is it's going to analyze all the scan data, and we're going to be able to segment it into different regions. And then we're going to be able to intersect all the regions and the CAD patches that we've created to build up our ideal CAD model. The other thing that we can do is we can rotate the blades on top of each other, so we can analyze any defects that might exist locally on one blade that we don't want to recreate in the CAD model, because we want to have a perfect CAD model that doesn't have any defects.
We can detect the damage and then analyze the data, reverse engineer it to design intent.
Exactly.
Get rid of those damaged areas.
Exactly. An old propeller like this is going to have a bit of damage, so we want it to be a perfect CAD model. But yeah, not just for reverse engineering. These scanners are also well built for inspection, which is going to be what Ben's going to be talking about, and he'll be showing us some ASUB scanning spray in that application as well. But we don't need ASUB scanning spray for this propeller because the surface is perfectly matte. So Ben will talk a little bit more about that.
Yeah, absolutely. That's great.
Okay, so again, we've scanned that side, which we're happy with. We're going to come here to cut out background points again. Let me just make sure I've selected the right thing. Yeah. So 1, 2, 3. Just make sure I'm happy with that. I am. Okay, so again, it's going to delete all that data. So what we've done now is we've scanned one side and we've scanned the other side. But if we were to look in the software, what we can see is that they're sort of on top of each other. They're not really well aligned. So what we need to do now is we need to tell the software to align them together to the same coordinate system. So what we're going to do is we're going to click this button here, and it's going to do it based on the common reference points. Okay, so we can get some quality feedback. We can see that we've got all green ticks. We're happy to do it. We can see these yellow reference points, which are the ones that have been used to do the alignment. We can just have a quick little visual check. It's looking all good. Okay, great. So once we've got that, we've got our digital twin. What we can do is we can start doing the reverse engineering. So this is the actual end result. This is the CAD model that we've created. As I mentioned, that was done in reverse engineered in Geomagic. And once we've got this CAD model, we can manufacture it anyway. We could have it machined by machinists. We could have it casted. We could also have it 3D printed, which is where I'm going to start talking about these 3D printers now. What I will do is stop sharing so hopefully you can see it. Yeah, this is the WASP 2040. We did actually print a propeller before. We seem to have just misplaced it. So you have to take my word for it that we did print one. Yeah, so this is the WASP 2040. It's so named after its build volume. So it's got a 20 centimeter diameter build plate, but it can print up to 40 centimeters high. We've got a bigger brother at the back of the WASP 4070. And again, it's got a 40 centimeter diameter build plate and a 70 centimeter high build volume. But there's also a bigger brother of that again, which is a 6100. And again, there's a 3MT above that. So if you're ever interested in 3D printing, please contact us. We are the Victorian resellers for WASP 3D printers. So any questions about that, please contact us afterwards. But I'm going to hand over to Ben now.
Yeah, wonderful.
And he's going to jump on to the next application.
Yeah, excellent. Thanks, Josh.
I'll get my stuff out of the way.
Yeah, so what we're going to do is just switch over the sensor, as I say, to the smaller measuring volume, the GOM Scan 1200. Now these sensors just plug and play, just USB straight into PC, so we can just switch it out and switch the next one back in. While Josh is doing that, I'm going to prepare the part. So what we're going to be scanning is just this little conrod right here. Now because this is a shiny surface, we're going to need to apply the spray. So we're going to be using the ASUB scanning sprays. We've got the different scanning sprays on the front here. I'm just going to use the blue. Now this is a disappearing scanning spray. So what it does is it actually dissipates off the surface after about an hour to 2 hours. So what that means is we don't need to worry about cleaning down parts. It evaporates off the surface, doesn't need any residue. So it's really nice and easy to use. So we just spray a bit on here, away from the scanner probably. Over to Josh, here we go. How's it smell, Josh?
It smells great.
It's lovely. Yeah, excellent. So we don't need too much. And what it does is actually, it kind of covers the surface really well. It's a really well designed spray. So it's really even finish. So what we can do is, reliably approximate how much surface we're adding to it. But it's, yeah, no, that's great. So what I'll do now is just place the part smack bang in the center of the rotation table. And what you can see is that projected area. So if you notice on the previous one, the 400, it was quite a large scanning area. This is a much smaller area. So we're concentrating these 5 million megapixel cameras just on a much smaller area, so we get higher resolution data. Let's just adjust that. So we've got the sensor right in the middle of the volume. And then we'll jump into the software again. And yeah, we'll start scanning. Any concerns of breathing in spray? Absolutely not. Yeah, it is perfectly safe. It smells wonderful. So yeah, no worries about that. We've got the full data sheets, and it is safe. It doesn't use titanium, so it's not.
It is free of titanium dioxide, so it's not carcinogenic. We can send you a material safety data sheet afterwards if you want, Guillaume, and share that with you. But it is safe. It's recommended to use it in a ventilated area, so we're probably just done breathing on top of each other is probably not the greatest, but it is safe.
Yeah. And just the other scanning spray. So the blue that I'm using here, dissipates in about an hour to 2 hours. The orange lasts a little bit longer. So we're talking like 12 to 24 hours. Yeah. So if we're scanning a large component, it's much better to use that because then you're not going to worry about it evaporating onto the surface whilst you're scanning. Yeah. The blue is great for small components we can scan really quickly. The white is permanent, so it doesn't disappear. I mean, it's permanent. It doesn't disappear. You just clean it off with a dry rag. Yeah. And then the green, which is on the end, is for air guns. So that's for really big components, maybe for automotive use, scanning a whole car. You can just use an air gun to cover that surface really, really quickly. But yeah, let's share my screen. We're going to go a bit wild again. Let's go entire screen, and then jump into my software. So again, using the GOM scanning software, I'm going to be using the workflow system. So I'll just initialize my scanner right here. So it's automatically identified the scanner. You can see the measurement area there. I'm just ignore my warm-up time because we're not worried about that. And we've got the reference points again on that surface. So again, using the workflow system, which is going to scan with rotation table, enter my measurement temperature, and it's going to do everything automatically. Set my exposure times and all of my capture all the reference points, and away we go. Just building up the scan data. As you can see there, nice and quick, really easy to capture some really good quality scan data.
Yeah, that's fine.
Yeah. So the next process would be the same as Josh showed you earlier. Scan one side, make sure we get all the different angles, get all the information, flip it over, scan the second side, and marry the two together. Now you've already seen that process, so I'm going to skip straight onto the inspection. But yeah, as you can see, that's the quality of data we can get straight off the bat. So yeah, what I'll do is I'll just dive into this project right here. Now this is a bit of scan data that was prepared by Olivia. Did a fantastic job scanning all these components earlier using these very same systems. So this is that full scan of the conrod. What I can show you here is the mesh structure. So what this really shows is the resolution of these systems. So every intersection of a line is a point captured in the space. So we've got, if we can see here in the information tab, just under 500,000 points captured on this conrod using this system. So it's a huge amount of data. Now, the applications for this are, similar to the propeller. What we can do is inspect this back to a CAD model. We can create a CAD model, or we can dimensionally inspect the part itself. So what we've got is actually the full assembly of this piston. So you can see here the piston head, and what we've got is a bit of damage here. So maybe what we want to do is inspect this conrod and detect any deviations that might have occurred from that piston. Can we reuse this conrod? So the important things would be maybe the cylinders in the end, the angularity between those, and then looking at maybe an inspection between the assembly itself. So we've got the CAD model here, which is right here. So what we can do is then start doing our dimensional inspection back to our CAD model. So this comes up as a color map. And you see the legend down the right-hand side. What we can do is inspect every area on this conrod back to the CAD model. Okay. And check all those dimensions there. But this is really just surface deviation. And for this conrod, the main surface is really irrelevant. It's mostly just the bearing faces that are important. So what we can do is create our features on our CAD model. So let's just create a couple of cylinders right here. So I'm just clicking on the surface, and then I'm going to fit those to my scan data. And why we do it on the CAD model is because then we're creating a template. So if we were able to rescan this component, everything here will be remembered. It will remember all these steps I'm doing here. So it would be nice and easy to replicate this.
Okay.
Yeah.
So you create your inspection of the CAD model first, and then you recreate the equivalent elements on the scan data, and then you can do the comparison between the two.
Exactly. So we create the one CAD model, and we fit them to the scan data using whatever parameters we want. So as you can see here, we can see the diameters of those two cylinders, which are pucker, absolutely spot on, no worries at all. So then what we maybe want to look at some GD&T. So as it does an autosave, maybe we want to look at a roundness check.
Yeah.
So we just do a roundness check again, just straight on those cylinders. This is going to do all of my GD&T calculation. I'll just need to input the tolerance, which is right here. So 0.1 mil is absolutely fine, and we can see that those references there. The thing with this GOM system though is because we capture so much data, we can go a lot further with the inspection than just looking at this one-digit answer. So what we can do is flick on this color deviation representation and maybe change our color band down to 50 microns. Now what this is going to show is a much more detailed understanding of what's going on within these cylinders. So this is looking at that GD&T feature itself and then projecting that back onto the CAD model. So what we can do is inspect every single feature on here and how that's affected by this roundness check. Okay. So you can see these score marks and these deviations. Now these are much smaller. I've had to change that color band on the right hand side to find those. Yeah. This is where we can start looking at part wear, maybe a part life cycle, maybe tool life over time. We can analyze those parts that it produced.
Okay. So we couldn't see that when we just did the color map back to the CAD model.
Yeah.
Okay, but we can see it when we do the comparison of the surface back to the roundness check itself.
Exactly, because this is not looking at deviation from the scan data back to the CAD model. Okay. That's just looking at like linear deviations. This is looking at the roundness and how that roundness is affected inside the cylinder.
Okay. So it's that means we can do the inspection without the CAD model.
Exactly that. Yes, okay. We can do both.
Great.
So another thing we've done is this digital assembly. So this is called a parts project, and you can see down the right-hand side, we've got these different areas of the Explorer view for these different parts. So I've got the piston right here, we've got the conrod, and we've also got the gudgeon pin, the lower pin, the bearings, and things like that. They're all in this one same project. What that means is we can do individual alignments and individual inspections on different parts of the assembly. So for example, we've got the lower bearing here. We can do a color map inspection on that lower bearing. But then what we can also do is align that back into my conrod and see how it's affected there. Other things we might want to try is if we look at our piston, maybe we've got the cylinders here for the gudgeon pin, and we want to see a concentricity check from that against our conrod. Mm-hmm. So this, if I find the right cylinder, we can have a look at here, and then again, what I say,
just to slow us down.
So if we just do a concentricity check, select my datum system, which we've already prepared, which is this piston datum here, and then we can check that deviation as a concentricity from the conrod back into the piston. So we can do these multi-part assemblies and multi-part analysis. Yeah. You know, an excellent application for this may be looking at a plastic injection molding tool. But what we want to do is check this as an assembled component and see how those mating faces are going to affect when the part is assembled. We can't physically see when we're capturing that data. So look at any interference of those two faces. Mm-hmm. But yeah, that is a very brief overview of the GOM Scan 1.
Yeah.
I think I've rocketed through my part a bit quicker than I was expecting, but yeah, maybe we'll dive in and see any questions, and we've got some other demo material we can look at as well.
Yeah. So that was actually doing comparison between parts. That was awesome.
Thank you.
Really cool.
Yeah, I know. Yeah, no, it is. It's a great scanning system, and really adaptable. You know, as I said, we can just plug and play these different measuring volumes depending on these different parts. Yeah. So we've got a large block, we can just throw in the
400,
the GOM Scan 1 400, scan at a larger volume, and then if we want that high resolution, that really fine detail, all that additional accuracies that we can get with the smaller measuring volumes, we can go for 200 or the 100.
Yeah. So we've shown today the 200 and the 400, but as Ben said, there's a smaller one, the 100 volume. But yeah, we have done that a bit quicker than what we anticipated. But if there are any questions, please put them in the chat window. I notice our friend Russ has let us know that the Aussies are 1 for 110, which is great.
Cheers, Russ.
Yeah. But yeah, feel free to ask any questions, put them in. I guess other things that are worth mentioning and repeating is that these are brand new systems released by GOM, I think earlier this year, only a few months ago. We've only just received them, so we're still putting them through their paces, but they seem excellent. What you're seeing here is a complete system. You get a studio stand, you get the sensor, a computer comes with it. It just plugs into a USB port on the side of the computer. The ROC 350 can come with it if you want it. It's an optional add-on, but recommended because, as you've seen, it greatly speeds up the scanning process.
Yeah. Well, maybe I'll dive back into the software. I'll show you some other inspection features, and if any questions come through, maybe Matt can just shout them out so we can see them. So let me reshare that, because there's you know, the inspection software is phenomenal. There's so many different features that we can use and we can do to get a really full understanding of the part. So we've already had a look at the conrod here. We've inspected the diameters. So you know, and using that as well as using these color maps and using the two together to get full understanding of the part. You know, how that compares back to a CAD model, but also the dimensions of that part itself. What we can also do is multiple alignments. So at the moment, we're just working in a pre-alignment, which is basically just a global best fit. Just puts the two parts close together, and what we can do is, you know, that's really used for getting an initial understanding of the part.
Yep.
You know, are we close? Do we need to carry on with the inspection, or can we just scrap the part and get rid of it straight away? But once we've done that, then we can do some more, you know, some better alignments. You know, some more, you know, maybe we're aligning back to a drawing, or you know, aligning back to an actual dating system.
Yeah, we got a couple of questions, guys.
Yeah.
Ben, what is the resolution achievable with each system?
It's wonderful. Luckily, Josh here is the master.
Am I?
Hit me up, Josh.
Yeah, I actually only know one of them off the top of my head. The GOM Scan 100 volume is 37 microns. The others are less than that. I believe the GOM Scan 400 is somewhere around that 40 to 50 micron range, 44 maybe. And I think the GOM Scan 200 is somewhere in between.
If only you had a spreadsheet.
If only I had the spreadsheet.
Yeah. We will get back to you with that.
Yeah.
The technical specs of that are will be available on the website. But yeah, essentially, the larger the measuring volume, the larger the point spacing. So
Yeah.
the larger the resolution. Yeah. So if you really need fine resolution, you go for the smaller measuring volume.
Yeah.
So you know, the parts that you've got down the front here, can't really see that, but you know, like the lower bearings and things like that. This will need either the 200 or the 100 to get this fine detail on these really small components.
It's about 15 mil in diameter or something like that.
Yeah, exactly. Yeah.
The other question we have is by Bo, what is the maximum scanning size?
Sure. So to be honest, you know, we can tile these measuring volumes. So essentially, you know, you can scan a part of any size, but that doesn't mean that you're going to want to. You know, we've got the GOM Scan 400 right here. So what we can do is capture that 400 mil area, and what we can do is just tile that to capture a much larger part. Now, every time you add in that tiling, you add in a deviation and uncertainty. So, you know, in general, we want to go maybe 4 times the size of that measuring volume.
Yeah.
Once you get larger than that, you probably want to use photogrammetry. Photogrammetry is a completely separate, standalone measurement system, and it basically controls the global environment by capturing the reference points.
Yeah.
And that's what we use to scan larger components. But yeah, in general, so you can expand the measuring volume of any scan by 4 times without any worry at all. Once you go larger than that, then you'd want to start introducing photogrammetry.
Sure. So for something like the GOM Scan 400, you can go up to 1.5, 1.6.
Yeah, probably up to some, you know, anything up to around 2 meters.
Yeah.
I think anything over 2 meters, you probably want to look at using a larger measuring volume, so a different scanning system, or introduce photogrammetry.
Yep. Great. Another question from Guillaume is, how does the Scan 1 compare to the ATOS-Q? What applications would you recommend the Scan 1? And same question for the ATOS-Q.
Yeah, excellent. So, you know, the ATOS-Q is GOM's mid-level system. So it's a really capable system. And the main difference is it's got adjustable measuring volumes. So whereas the GOM Scan 1, we've got these standalone measuring volumes. So we want to switch between them. It's a complete unit change. Yeah. The ATOS-Q, what we do is we just switch out the lenses and recalibrate to adjust those measuring volumes. So the ATOS-Q is it's a very adjustable system. You know, we can really tailor it for these specific applications and switch it between applications. Whereas this is more, you know, we pick the right system for this job. The other thing is that there is a difference in the projection technique. So this is using a kind of a standard blue LED projector. The ATOS-Q uses an LED projector through an LCD screen, so it's very high definition projection. So we do get slightly better accuracies, but they're both very capable systems. Yeah. I think, you know, if you're using a system for a wide range of applications, then it's probably something like the Q. If you've got a small selection of applications that you want a really reliable system for, then a GOM Scan 1 would be very suitable. Yeah. There's also, you know, budgetary considerations and things like that.
And resolution, the GOM Scan 1 is only 6 megapixel system, whereas the ATOS-Q can come in an 8 or a 12 megapixel version. The GOM Scan 1, as Ben sort of alluded to, there's a slight difference in projection. The GOM Scan 1 doesn't have a feature called triple scan, which the ATOS-Q does. The triple scan is a way that essentially taking 3 measurements at one time, what both cameras are seeing, what the left camera and the projector are seeing, and what the right camera and the projector are seeing. and that allows you to capture data much faster. You can do a lot more data.
Yep.
With each measurement.
Exactly. It's perfect for capturing like deep bores and pockets where we can actually use each camera individually to capture the data down inside those areas.
Yeah.
And yeah, things like reflection detection where we can automatically detect areas of reflection, mask those out. Those are available with the Atos Q.
Another consideration is if it's something that you see in the future with your scanning system, the GOM Scan one cannot be automated, so it can only be in this sort of configuration, a manual or a semi-automated setup, whereas the Atos Q can grow up with you in terms of growing to an automated system, whether that's a GOM Scan cobot or a scan box.
Yeah, so a fully automated system with a robot cell in it. Yeah, calculates all those measurement positions automatically.
Yeah.
Yeah.
I'll wait for a little bit longer. There doesn't appear to be any more questions at this stage.
Any questions from in the house? We do
have some people here, which is nice.
Yeah. No resolution, depth, accuracy, maybe?
Yes. Yeah. The easiest question, thank you. So accuracy is incredibly difficult with these kind of systems. As in difficult to give definitive answers for, and that's because there's so many variables. What we do is we do in-house testing, and we kind of can approximate what kind of accuracies we can get with these systems. The GOM Scan 100 and 200 can both achieve repeatabilities of sub 10 microns without too much issue.
Yeah.
And we can get accuracies better than that. It's when we start controlling the environment, controlling the temperature and things like that. That's when we get really, really good accuracies. But they're all very capable systems. GOM doesn't make systems that aren't accurate. That's not in their wheelhouse. It's got a ZEISS label on it. It's got a GOM label on it. It's great technology.
It's accurate.
Yeah.
What's the process for like stitching? If you're taking a number of shots to get a bigger volume, what's that process?
Sure.
Yeah.
So in case people didn't hear the question was, what is the process of measuring an object that's bigger than the field of view? So for example, what we've seen today is the scanner is looking at an area on the rotation table, and that's just rotating, okay? So there's no manual interference. Let's say if we wanted to measure something that was the width of this table, right? We'd have to start with the scanner looking sort of here, right? And then we'd have to move along with each measurement. So we take one measurement, we'd move the stand and the sensor to the next position. We've got a decent amount of overlap, common reference points between that last measurement and the new measurement, and just keep tiling along until we've captured the entire length of it. So it's a bit of a manual process.
And then when you go to put it together at the end, is that much?
Yeah, so it's sort of an iterative process, whereas the first measurement would capture an area, would also capture reference points within that area. Then when we move to the next area, we need to make sure that the scanner and software can see an overlap between the new area and the previous area. So it'll see common reference points that it's last seen, and we'll now know how to stitch it to the previous one. If I started here and then just went over there, it wouldn't know anything there that's similar.
But yeah, that transformation is all done automatically within the software. So it's a traffic light system, so it shows you essentially, it's red, yellow, or green, and green or happy, yellow there might be a slight transformation. Maybe we want to capture a measurement in the middle, and red it just means that there's no link between those two measurements.
And so say then you end up with a scan at the end where it's missing something. And you can see that in the model that you've created for the mesh. You can go back, you could go and add that in.
Yeah, absolutely. Yeah, you can go back and add in data at any time. Because it's got those reference points, you can just add in bits that you need. And yes, that's absolutely fine. Yeah.
As you join scan together, say 6 of them, you can't be sure that everything nice and linear. How do you correct it?
Yeah, sure. Well, let me show you, because there's a number of features in the software that help with that exact process.
Just to clarify what the question was, in case people didn't hear, the question was, my understanding was, how are we certain that we're measuring accurately as we transition from one spot to another? Is that right? Yeah.
Accumulated errors.
Yeah.
Sure. So the system does a number of things. So what we get is these quality parameters you can see on the right-hand side here. And this is for every individual scan. So this is looking at how well that scan is actually completed, how well it's kind of, it's referencing back to the reference point. So we've captured the reference point and then we capture it with this scan. Is there any deviation between those two? And that's right here in this transformation deviation. Now we get this for every single measurement, including lighting change, temperature change, any movement during that measurement, and all of those quality parameters are held. And it's against this traffic light system.
So for the benefit of those who can't see the screen at the moment, just want to sort of give us some kind of, there's a numerical value.
Yeah, sure. So the transformation deviation for this one scan is 4 microns. and then 3 microns, 3 microns, 3 microns. So this is all the individual deviation for that individual scan. Now we get, once we've completed that full scan, we get an overall residual for that full measurement series. In this case, 2.5 microns. So that's for this whole section of that scan. In this case, this piston looking at this top side of it.
Yeah.
And we've got this, the two sides, so we've got 2.5 microns on either side, and then we transform both of those together using the process that Josh showed earlier, using those reference points, common reference points on the side.
Yeah.
But using these figures, these transformations and these residuals, we can get an understanding of the kind of accuracies that we can hit.
Yeah.
So in this case, any residual over maybe 20 microns, we'd be concerned. In this case, with 2.5 microns, we're very confident that we're capturing good, accurate data.
2.5 micron, what's the size of that?
Is it?
Sorry.
What's the actual size?
Smallest.
Yes, this is this small piston right here. Yeah.
And that's for the GOM Scan 100, the smallest measurement volume.
Yeah. But the other thing we get with the capture is actually all of the measurement images are captured and held within the software. So that's right here. So these are all the actual live images from the capture. So we can look at those images. We can maybe use this to identify any serial numbers or look at how the part was set up. We can also look at the individual reference points captured on each one of those images and the deviations associated with them. So let's say something's moved. We can go back in here and find out what's moved, eliminate those reference points, and still get the same accuracies, even though we can maybe have a slight transformation deviation. We can go back and do all this analysis. And this is held within the software forever. All of this information is always available. So, 6 months' time, maybe you get an error. Someone's identified a defect. We can go back and look at exactly how that part was set up. If it was a sheet metal part, we can check all the clamps were engaged on the fixture and those kind of things. But yeah, all of that kind of information is held within the project as standard, and that goes for this scanning system, but any scanning system that GOM make.
Yeah. We have another question from Lachlan. So highly detailed part scans without a problem.
Yeah, absolutely. Yeah, it's just selecting the right scanning system. So if you need that detail, we select a smaller measuring volume that's going to capture enough detail on that small feature.
Yeah, exactly. It's you're matching the system to the application, or matching the measurement volume to the application. If you've got high detailed parts, then we'll take a look at that and discuss it together which system is best. But suffice to say, the smaller the measurement volume, the more detail, the more resolution you're going to capture.
Yeah, excellent.
I think that's it. Russ hasn't given us another update.
No, they're probably on that.
Probably no wickets though.
Probably
Just one more question.
Yes.
Yeah.
The system needs to be calibrated. Is that automatic?
It's a great question. Carry on. You answer that. I'll
Okay.
And then.
So the system does need to be calibrated, correct? All the systems are shipped with a calibration plate that comes with the system. And essentially it only takes 5-10 minutes at the start. Essentially all you need to do is move the scanner through a series of positions relative to the plate, and then the software will remember that sort of configuration. The situation is the relative positions and angles of the cameras. This is the calibration plate. For those that can't quite see that, there's a series of black ellipses which have been etched onto the surface.
So yeah, we've got a different one of these for each measuring volume. So we want to calibrate the 200 mil. We use the 200 mil calibration panel. We take about 18 measurements of this panel.
Yeah.
It takes about 5 minutes, and then the system's calibrated and ready for use.
And it should be fine to keep using, but because it only takes 5-10 minutes to calibrate, it's sort of recommended to do it at the start of every day because it's such a quick process. But nothing really should change the calibration unless you give it a bit of a bump. When Australia is 1 for 500 and Ben's really upset, he'll punch the sensor, and then we'll say, no, Ben, no, you can't do that because you now have to recalibrate it.
Okay. Do I recalibrate you as well?
So more question about the calibration. When
Yeah.
you do the calibration, do you put that plate at right angles to the camera?
Yeah, exactly. So you start off at right angles, and you take measurements all the way through the measuring volume, and then you change to a certain number of angles. Now it's all done within the software.
So you have to do calibration different angles.
Yeah, exactly. So you do about it's about 12 different measurements through the measuring volume, so at right angles, and then another about 6 at different angles to calibrate it. But the software is actually it shows you where to position the sensor, and then it gives you like a big green tick when you're in the right place. So it's a nice, easy process, and once you get used to it, you do it very quickly. The systems are also calibrated in Germany. There is a VDI/VDE certification, and this is calibrated using a bull bar, and this is done before it's shipped. They basically just take measurements of a bull bar, reference that back against the nominals, make sure that it's scanning accurately, and that's done back in Germany. So yeah, these two processes, the VDI/VDE certification and the in-field calibration, both make sure that it's certified back to national standards.
But there's a lot of other measurement systems will require calibration of the systems we sent back to the manufacturer. You don't have to do that because the system's sent with the calibration panel, so you do that in-house whenever you feel like it.
Yep. So yeah, a couple more questions. So Russ, there's several sizes of rotation tables there are. So there's two different sizes. This is the GOM 350. There's also the GOM 650, which is obviously larger, can handle bigger components. But there's no difference. They both USB input straight into the software and really easy to operate. And then yeah.
Another question from Ben: does using the sprayer allow measurement of glass or mirror components? Yes, exactly. So transparent parts and glass components are the hardest things to measure in 3D scanning because or any sort of measuring process, because the light that you put on the surface actually penetrates through there, and the cameras can't make sense of the surface. So we have to matte it out. We have to make sure that the surface is opaque, not transparent. So we apply a white spray to it.
Can you do a very good video showing the spray of an automotive headlight?
Yes, we do have. We've got a nice little spray of the ASA blue in action on an automotive headlight. Yeah. Good work done.
Thank you very much, mate. Yeah.
Great. Doesn't seem to be any more questions. Mike, wait. Yeah, sorry.
You mentioned about automating the system with like a robot or something like that. So what would that? And what would you use that for, and what would that look like? What would you be doing?
Give me a second, I'll show you what it looks like. Put me on the spot, Josh, explain.
It's mainly used.
Yeah.
It's mainly used for series production. Okay, so you're a manufacturer that's producing a lot of components, and you want to measure a lot of them. Okay, so 3D scanning in this sort of sense could be a bit slower. All right. But you need to set up the scanning so it happens a lot faster. So what you do is you invest in a robot, and the scanner sits on the end of that robot, and the robot takes 5 minutes less, 3 minutes sometimes, to measure an entire component, generally pretty complex components. And then because the software is also automated, once you've collected the scan data automatically with your robot, the software automatically generates all of your inspection results. So within a couple of minutes of loading your part into the scan box, as we call them, you've automatically got a green tick for pass or a no, not ready to go. Yeah,
exactly. So this is the full range of the scan boxes, and they're all supplied by GOM as a complete inspection cell. So it's all loaded in as a cell. So we've got the robot, the sensor, and the housing, and everything comes in as a complete package. That means we can get them installed and up and running very, very quickly. And because it's kind of uniform and it's the same scan boxes. They're all around the world. So they're very the software and the interaction between the hardware and the software is very good. The main difference between all these scan boxes is simply the size of the part we fit on them. So the Cobot and the Series 4, which are in the top left, they can fit parts up to around 500 mil, and then the larger ones, we can fully automate anything up to 10 meters long. So the process of programming these automated systems is again all done with the GOM software. So if we've got a CAD model, we load that into this virtual environment. It's called the virtual measuring ring. And then the system will position the sensor in the right place to capture the highest quality data all automatically.
So in that picture that you've got up there, that Surface Series 8, is it 8?
Yep.
What's that measuring there?
So that's measuring a full car body.
That's right. So that is a practical thing.
Absolutely.
And that's using one of these?
It's the bigger brother, essentially.
Yeah. So it's called the Atos 5. It's the bigger brother of the Atos Cube, and that's simply because of the measuring volume. We want to scan a large measuring volume, especially for the sheet metal components.
And so what's the volume? What volume would that one be?
So that's using a 1 meter measuring volume.
Oh, okay,
probably.
Right. And that's practical for something like that size sort of thing.
Yeah.
Okay. But the complex companies that get Scanbox Series 8s are Fords and BMW and Volkswagen that need to have this. And
I think they're also being used by Bombardier to scan rail bogies and things like that. This Series 8 has actually got different measuring cells you can see on the left and the right hand side. So it's one robot that's kind of servicing two cells, so we can do really, really quick scanning.
So You can load the car body in the middle, both robots will scan that at the same time, and then while that's happening, you can load 2 parts into the left and right wings as well.
Yeah.
So then when it's finished scanning, the robots can go to the other side. Yeah.
But you could do that manually as well, then really.
Yeah, absolutely, yeah.
It'd be slower, a lot slower.
But yeah. But
Yeah.
it's-
So usually, for time saving, we look at, if we're comparing against a CMM, from CMM to a manual system, we'd probably save around 50% of the time.
Yeah.
And then if we look at automating that, we'd save another 50%. So it's significantly faster than scanning it manually, but also we get the incredible accuracies. We can hit, phenomenal accuracies with these automated systems. One of the biggest considerations is the position of the sensor to capture that data. And if we can, position that sensor in exactly the same place every single time, then we can get, accuracies of, single-digit microns without too much consideration.
Yeah. Okay.
Yeah. We've got any more questions? Any more updates on cricket?
We got Aman saying hands-on metrology
Yeah,
website
yeah,
would be a
yeah.
nice resource to mention.
So just the question, so you don't have to recalibrate every time you move the sensor? Absolutely not. And the system actually tells us when we need to recalibrate. So it comes up with a warning saying if it is decalibrated, that you need to recalibrate. And that is that process that we showed you earlier of measuring that panel. But yeah, it doesn't have to be done every time. And especially these kind of systems that are fixed measuring volume, there's not much that can go wrong with them. And like Josh says, as long as they don't lose the cricket and someone gets angry with it, they're not going to decalibrate very easily. And yeah, if it does, it comes up with a message, takes 5 minutes, you recalibrate and you keep on scanning.
Sure. Just a quick reference for everybody. There is a great website that is being produced by both GOM and both GOM and ZEISS called Hands on Metrology. So it's a sort of collaboration between GOM and ZEISS. It's just got a few GOM systems and a few ZEISS systems on there. But there's a lot of informative resources on here. There's use cases. There's MMG who use one of the ZEISS systems, the T-Scan Hawk. So there's use cases by people internationally using the system, as well as a lot of tutorials on how to use the software, what to do when you get your system, opening up, unboxing it, your first use, running through the software and how to do the analysis, all these types of things. So it's a really great educational package for anybody, not just people who purchase the system, but anyone who just wants to use even GOM Suite to do inspection themselves. Because another point is that the software we've been using is free to download. Anybody can download it right now. You can download it, and if you've already got a different type of scanner, you can load in your scan data into that and do your own inspection with it. Okay?
Wonderful.
Thank
Thank you very much.
Thank you very much.
So yeah, any other questions then please email us.
We'll walk over those.
Yeah.
Okay.
Wonderful.
Thank you
very much,
everybody.
everyone.
This will be recorded, so we'll send you a link to this.
Brilliant.
Thank you.
Thank you very
Bye,
much.
guys.